Good morning. So in the last lecture we were concerned with finding out what functions we really want to use when we define the semantics of Haskell. Now let's see, maybe this is better. And we've seen that we don't want to use all functions. We have already made one restriction to monotonic functions. And we introduced another restriction to so-called continuous functions. Now let's recapitulate what we did. We restrict ourselves to domains where this less defined or equal relation is complete. So it's a complete partial ordering. Complete means, well, first of all, you must have a smallest element, which we denote by a bottom. And then, most importantly, every chain must have a least upper bound. And that will be our goal, and today we will finally arrive at this goal. We will show how to define the semantics of recursively defined functions. We will do this by giving a chain, and then the semantics is defined to be the least upper bound of this chain. And in order to be sure that this least upper bound exists, we need the ordering to be complete. Now, moreover, we restrict ourselves to continuous functions. Now, what does continuous mean? Continuous means the following. If you have a chain like this, so D1 is less defined or equal than D2, and so on, then this chain has a least upper bound. Let's call it D. And what you could do is you could first build this least upper bound and then apply F. If you do this, you arrive at F of D. Now, if F is continuous, then you can also do it the other way around. And the other way around means you first apply F, so you apply F to each element of this chain. So if you apply F to D1, you get F of D1. Here you get F of D2, and so on. And afterwards, you build the least upper bound. And if F is continuous, then you arrive at the same element. So it doesn't matter whether you first build the least upper bound and then apply F, or if you do it the other way around, first apply F to each element in the chain and then take the least upper bound. Now, this is the notion of continuous, and we have seen what the connection between continuous and monotonic is. Continuous is stronger. So if F is continuous, then F is also monotonic, but not vice versa. We have seen an example of a function that is monotonic but not continuous. And we have also seen that, well, we have some domains already fixed. We take, for the base types, we take these base domains, Z bottom, the Booleans with bottom, and so on. Here, the less defined or equal relation is complete. Similarly, for the domains that we take for tuples. And for functions, we will now take the set of all continuous functions. Not the set of all functions, but just the continuous functions. We denote them by these angle brackets. And indeed, we will now give a theorem which says that even on this domain of just the continuous functions, this less defined or equal relation is still complete. Now, this is not completely trivial. So what we have shown is that this less defined or equal relation on a set of all functions is complete. So this is a complete partial orderer on the set of all functions. Now, this does not imply that if we take a subset of the functions, only the continuous functions, that this is still complete. This does not immediately imply that this less defined or equal relation on just the continuous functions is also a CPO on the continuous functions from D1 to D2. Now, why is this the case? So complete means you have a smallest element, and moreover, every chain has a least upper bound. And this least upper bound, for every chain, has a least upper bound. This least upper bound must be contained in this domain D. And now you can imagine that there are subsets, so sets which do not contain all functions, but just some functions, where you can build a chain of elements from this subset, but the least upper bound is not in this subset. So there are subsets of D1 arrow D2 where this less defined or equal relation is not complete. For example, so there are subsets of D1 arrow D2 where the less defined or equal relation is not complete. And one example is the set of total functions. So the set of all total functions is clearly a subset of all the functions. So, for example, the set of all total functions. Now, you probably remember this leading example that we had with these fact0, fact1, fact2 functions. Sorry, not the set of all total functions. Let's take the set of all non-total functions, the set of all partial functions. Now, why is this the case? Well, we had a chain here, fact0, fact1, fact2. And fact0 was less defined or equal than fact1. This was less defined or equal than fact2, and so on. And all of these functions are partial. So all of these functions are non-total. There exist arguments, different from bottom, where fact0 is not defined. There is also an argument where fact1 is not defined. There's also an argument where fact2 is not defined. This is not defined for x greater or equal than 2. Fact3 is not defined for x greater or equal than 3. So they are all partial. So this would be a chain of functions also for this subset where we restrict ourselves to non-total functions. Now, if this ordering would be complete on non-total functions, this chain would have to have a least upper bound, which is also in this subset. Now, we know how the least upper bound of this chain looks like. So the least upper bound is fact. So it's this function down here. But this function is total. This function is defined everywhere except for bottom. So it can happen that a chain of partial functions has a least upper bound, which is not partial but total. And therefore, the subset of partial functions, there, this less defined or equal relation is not complete. So since fact is total, it is not in the subset, and therefore we can see that for the set of partial functions, so for the set of partial functions, this less defined or equal relation is not complete. So not every subset, if you take a set where less defined or equal is complete, that doesn't mean that it's also complete for all subsets. But for the subset of continuous functions, this is indeed true. So basically this means if you have a chain of continuous functions, then the least upper bound is also continuous. And that's the next theorem. So this is theorem 2116. And it says, it gives us the completeness of the function domain. So let D1 and D2 be domains where this less defined or equal relations are complete. So this relation and this relation are complete partial orderings. Then the set of all continuous functions from D1 to D2 is the corresponding function domain. And the less defined or equal relation on this function domain is complete. So this is a complete partial order on the continuous functions. So the main thing one has to prove here is that if you have a chain of continuous functions, then the least upper bound is also continuous. So the proof I will omit I will omit this. It's in the course notes, so if you really want to read it, it is in the course notes. It's not too difficult, but a little technical. So the idea is show that the least upper bound of a chain of continuous functions is also continuous. Okay, so I omit the proof here, but in the course notes you can find it. Okay, and now we have all we need to define or to illustrate how we define the semantics of a function that is defined by recursion. Okay, so the key idea will be, on the one hand, we use this notion of chain and least upper bounds, and on the other hand, we use the notion of fixed points. And that's the reason why this last section in this subsection 2.1 is called fixed points. So what we've done now is in 2.1.1, we spoke about partially defined values. Here we had partially defined values. We needed this. So partially defined values. We needed this to introduce things like bottom and things like the less defined or equal relation. And in 2.1.2, we basically introduced notions like complete, monotonic, and continuous. And this, in particular, we needed to, in the end, define the domain of the functions that we look at. And the domain for functions are just the continuous functions. So here we had monotonicity, continuity, and completeness. And in particular, we defined the function domain. So the domains for functions are just the continuous functions and not all functions. And now we can finally say, if we have a Haskell program with recursion typically, then what will be the semantics of the function that is defined in this Haskell program? So our goal is, if we have a Haskell program which defines some function, and typically it is defined by recursion, and then determine the semantics of this function, the denotational semantics of this function. Let's start with an easy example. So the easy case is if there is no recursion. So case one is functions without recursion. Okay, let's look at an example. So I write down a Haskell program without recursion, very easy one, and then we think about the semantics, and that will be very straightforward. So let's take a Haskell program which converts booleans to integers. So it's a Haskell program from bool to int, and it works like this. True is converted to 1, false is converted to 0. Usual conversion. So conf is a function, it takes a boolean b, so it's lambda b, and it returns, well, it checks if b is true. So if b is true, then it returns 1, and else it returns 0. Of course, I could also write conf of b equals this if expression, but there's some reason for writing it like this. It's equivalent anyway. And you're used to lambda notation, so you should not be confused by this. Okay, now luckily this program is not recursive. So conf appears on the left-hand side, but not on the right-hand side. And so, well, the basic idea of the semantics is conf is just a function symbol. a Haskell function symbol. So we want to map this conf to a real mathematical function, and this mathematical function should satisfy this equation. In other words, if we replace conf by a real mathematical function here, and if we replace the functions that occur over here, so things like, well, the if statement or true or false and 1 and 0, if we replace them by their semantics as well, then the thing that is on the left-hand side should be the same as the thing on the right-hand side. So the idea is the function symbol, so the syntactic function symbol conf should be, by the semantics, it should be mapped to some real mathematical function. Should be mapped to a real function which satisfies this equation. Which satisfies this equation, namely the function on the left-hand side must be the same as the stuff on the right-hand side. Satisfies the defining equation of conf. Now, in this easy case, everything that is on the right-hand side here is predefined. So luckily, conf does not occur in the right-hand side. There are only predefined things here. There are predefined integers, 0 and 1. There are predefined values of type bool, like true. And what the meaning of the if construct is, well, okay, this if is also predefined. So this right-hand side only contains predefined functions. So since the right-hand side of this defining equation only contains predefined constructs of Haskell, we can, in this example, assume that we know their semantics already. So the semantics of this sign here is the integer number 0. The semantics of this sign is the integer number 1. The semantics of this thing is the Boolean value bool. And the semantics of the if statement is a function which is not very surprising. It takes 3 arguments. First one is the condition. If the condition is true, it returns the second argument. And if the condition is false, it returns the third argument. So the semantics of all this stuff we can define, because, I mean, Haskell has just a finite number of constructs. So we can say this semantics we already know. The problem is, how can we then determine the semantics of user-defined functions? And the user defined this thing. So we now have to say, if we know the semantics of the predefined constructs, how can we then come up with the semantics of the functions that the user has defined? So here we can assume that we already know their meaning, know their semantics. And the goal is, from this semantics, we should be able to deduce the semantics of user-defined functions. Now, what is the semantics of this expression on the right-hand side? So semantics of this thing, so of lambda b arrow, if b equals true, then 1 else 0. Okay, let's assume we know the semantics already. And the semantics of this is the following function f. Now f is a function from, what should it be? Basically, this should be a function from booleans to integers. Now the domain for booleans is b bottom, and the domain for integers is z bottom. So the semantics of this expression is a function from b bottom to z bottom. And how does this function look like? Okay, so there are 3 possibilities for b. b is from Boolean bottom. So b bottom has 3 elements, true, false, and bottom. So if b is true, then the result will be the integer number 1. If it is false, it is 0. And if it is bottom, then the result is also bottom. Now, this we know because we know the semantics of if. That is the semantics of if. The semantics of if means look at the condition, and depending on the condition, the result will be either the stuff that comes behind then or the stuff that comes behind else. And if the condition is not defined, then the semantics of this whole expression is undefined. And if we now suppose we know this already, then if the user writes a function definition like this, then the effect is that conf will get the same semantics as the stuff on the right-hand side. So the semantics of conf is this function f. So by the above definition, conf gets the function f as its semantics. So if we have a non-recursive definition, we hopefully already know the semantics of the right-hand side, and then if we write something like this, what happens is that this function symbol conf now has as its semantics this real mathematical function which goes from these values to these values, and it is defined like that. Now, unfortunately, most interesting functions are defined by recursion. So in reality, it's a bit more problematic. So now let's look at case 2. Now we have functions with recursion. Okay, here's an example, and it's the factorial function. So the factorial function is a function from int to int. And I define it like this. Now, again, to make life easy, I will only write fact on the left-hand side, and I will define it via a lambda expression. So fact is a function which takes an integer, so it's lambda x. And now it checks. If x is 0, so the factorial of 0 is 1. Now, in my definition of factorial, the factorial of negative numbers is also 1. So if x is less than or equal to 0, then the result should be 1. And else, I call fact recursively. So I call fact with x minus 1, and I multiply the result by x. Now this is how you would define factorial. Okay, and now I will give two possible ways to define the semantics of such a function. And then afterwards I will show that both these ways lead to the same solution. So I will give two alternatives how to define the semantics of fact. And then show that these two alternatives in fact are the same. So if you like one alternative more than the other, that's fine, because both alternatives give you the same semantics. And then show that both are equivalent. Okay, so alternative 1. Now, let's try to do it in the same way as we did it for conf. For conf, we said conf, so this function symbol conf, should be mapped to a function which satisfies this equation up there. And we want the same thing here. So fact, this function symbol fact, should be mapped to a function which satisfies this equation over here. So fact should be mapped to some function f. Now we know already on which domains f has to operate. So fact is a function symbol of type int arrow int. And we know the domain corresponding to int is z bottom. So the semantics should be a function from z bottom to z bottom, which satisfies the defining equation of fact. Now, how did we achieve this goal when we looked at conf? When we looked at conf, the good thing was that we already knew the semantics of the right-hand side, because the right-hand side only contained predefined functions. So what we did was we computed the semantics of the right-hand side, and then we said, this is the semantics that we want to assign to this function symbol on the left-hand side. Now, for fact, this is not possible because we don't know yet how the semantics of the right-hand side looks like. I mean, we know less than or equal is predefined. So the semantics of less defined or equal, we know. And the semantics of if, we know the semantics of 0 and 1, and of times, and of minus. But here we have fact. Now, the semantics of fact, we do not know yet. That's what we want to determine. We want to find out if we know the semantics of all predefined functions, how could we then define the semantics of fact? That's what we want to solve, this goal. And therefore, we don't know yet what the semantics of this right-hand side is because it contains fact. So, since the right-hand side contains fact itself, we do not know its semantics yet. So that's bad. We know how to deal with non-recursive definitions, but this definition is recursive. And therefore, we cannot just say, okay, let's first compute the semantics of the right-hand side and then say, this is the semantics of the left-hand side. And now the first idea how we can solve this problem is we can replace this definition of fact by a series of non-recursive definitions. Because we know how to deal with non-recursive definitions. So, solution, replace the definition of fact by several non-recursive definitions. Because non-recursive definitions, we know how to deal with this. Okay, how do we do this? We need one more function symbol. Bot is a function symbol. Should be a function symbol, a constant. Should be a constant, a Haskell constant. And whose semantics is bottom. So this bot symbol should always be undefined. So bot stands for undefined. So for example, if you want to define bot in Haskell, you can, for example, do this like this. Bot has type A, and you define bot equals a bot. Now, if you define this in Haskell and you want to evaluate bot, then you run into non-termination, so you can be pretty sure that this is undefined. So it is not difficult to write a constant in Haskell whose evaluation is undefined. This would do it. Okay, this we need. And now we can replace this definition of fact by several non-recursive definitions. Now the first function that I want to define is called fact0. And fact0 is the following function. It takes an integer, x, and it returns a bot. And the idea is these functions should be approximations to the real factorial function. They should do almost the same as factorial, but there are some elements where factorial would be defined, whereas these approximations are undefined. Now, this is a very bad approximation because this is always undefined. If you apply fact0 to some integer, it gives you bottom, so this is never defined. Now, the next approximation is better. It is called fact1. And it is defined like the factorial function. So I copy this definition here. The only difference is I don't want recursive calls. So fact1 will not call itself recursively, but instead of writing fact1 here, I will write fact0. So that's the only difference. So this is, I will write down the right-hand side. So fact1 is defined like fact, but instead of writing a recursive call here, I write fact0. Let me do this. So if x is less defined or equal than 0, then I return 1, else I return fact0 of x minus 1 times x. Now, what does this thing compute? Now, this one here is always undefined, fact0. This one here is a bit more defined. This is defined for all x's which are less than or equal to 0. For x less than or equal to 0, it returns 1. Otherwise, it would return this stuff here, but fact0 is undefined, so it would be undefined here. So this is undefined for x greater or equal than 1. Now, fact2, again, looks almost like the factorial function, but I don't want it to be a recursive definition. So fact2 will not call fact2, but fact2 will call fact1. So again, I copy the definition of factorial, then 1 else. But now the recursive call is not fact1. The recursive call is not fact2, but I call fact1. So in the recursive call, I always use not the current approximation, but the approximation that I had before. So here I have fact1. And now you can easily see that this is undefined for x greater or equal than 2. And so on. So I come up with infinitely many approximations. Fact n will call fact n minus 1 instead of a recursive call. And they are all non-recursive. So this thing has no recursive call. Fact1 does not call itself recursively. It calls a function that we had defined before. So, okay, and we continue this. So we have infinitely many approximations. So fact0, fact1, fact2, fact3, fact4, and so on. And so what we can see is fact n is defined using fact n minus 1, but it does not have recursion. So since it does not use recursion, we can now find out the semantics. So the semantics of fact n can easily be determined as before. So the semantics of fact n is the function fn from z bottom to z bottom. And how would the semantics look like? So for f0, f0 should be the semantics of fact0. Fact0 is defined like you can see up there. So it's a function, so the definition is lambda x arrow bot. Now we have said that bot should be a Haskell expression whose semantics is always undefined. And then if we know the semantics of this lambda construct, then we know what the semantics of fact0 is. It should be the function which always returns undefined. So this is undefined for all x from z bottom. Now, what is the semantics of fact1? Now, fact1, we proceed as we did it for conf. We look at the right-hand side. Now, the right-hand side only contains things where we know the semantics of. It contains if and less than or equal, and it contains fact0, but we know the semantics of fact0. This is the semantics of fact0. So since we know the semantics of fact 0, we can also say what the semantics of this right-hand side here is. So what is the semantics of this right-hand side of here? It's a function which takes an integer. If this integer is less than or equal to 0, then the result is 1. And otherwise, it is the semantics of this stuff here. So the result will be 1 if x is less than or equal to 0. And otherwise, it is the semantics of this expression. Now, the semantics of fact 0 is it's always undefined. And therefore, if we multiply something undefined with something else, the semantics is again undefined. So it is undefined otherwise. So we can determine the semantics because we know the semantics of fact 0. So here this is possible because we now know fact 0's semantics. Now again, for F2, for fact 2, what is the semantics? Well, luckily we now know the semantics of fact 1, it's this. And therefore we can also find out what the semantics of fact 2 is. So what is it? It is the function which gives us 1 if x is less than or equal than 0. And if x is not less than or equal than 0, then it gives us the semantics of this stuff over here. Now the semantics of fact 1 is f1. So if x is 1, then x minus 1 is 0, and fact 1 of 0 is 1 by this. So it gives us 1 times 1. It gives us 1 if x is 1 and undefined otherwise. So in other words, this gives us factorial of x for x less than or equal than 1 and undefined otherwise. And so on. So for Fn, we will then get factorial of x for x less than or equal than n minus 1 and undefined otherwise. So we have seen these functions before. This is what I called fact 0, fact 1, fact 2 on this slide over there. So this is the example that we had before. Okay, and since all these functions are defined without recursion, it is no problem to determine their semantics. Now, we have already seen that these functions, f0, f1, f2, f3, they form a chain. So, now this is always the case. If we build this approximation like this, then the semantics of these approximations will form a chain. So they form a chain. In other words, f0 is less defined or equal than f1, this is less defined or equal than f2, and so on. And now we know that these functions here, they are all computable, hence they are continuous. We know that this less defined or equal is complete on continuous functions, which means that this chain has a least upper bound. So there is a least upper bound of this chain. And the idea for the semantics is, if we have a recursively defined function like fact, then we take these approximations, we build the semantics of these approximations. These functions that we get as semantics, they form a chain, and we take its least upper bound, and that is the semantics of fact. Of this chain. And the idea is define the semantics of fact to be this least upper bound f. So in our example, we know how this f looks like. Here, f of x gives us factorial of x whenever x is not bottom, and it gives us bottom if x is bottom. So this will be the semantics of fact. So to recapitulate, what we do is, if we have a recursively defined function, build a series of non-recursively defined approximations to the recursively defined functions, compute their semantics, compute the semantics of these approximations, and then take the least upper bound. So here we had these approximations, fact 0, fact 1, and so, fact 0, fact 1, and so on. Compute the semantics. The semantics were functions that I called f0, f1, and so on. And then take the least upper bound of these approximations. So this would be the least upper bound of f0, f1, and so on. And this is the semantics of factorial. So this is alternative 1. Now, let's make it more precise. How do we get these approximations? So how do we get these approximations? These are these approximations which are almost like the factorial function, but in the recursive call, they don't have a recursive call, but instead they use the last approximation that we had before. Well, basically, you can say we start with the completely undefined function, fact 0, and then from one approximation to the next, we refine it. So we always start with a completely undefined function. Start with the completely undefined function. And then refine it step by step. Step by step. Now, how to refine it step by step? We can define a Haskell function which does this refinement for us. We don't have to do it by ourselves. We can express this as a Haskell function. This refinement can be expressed by, for example, Haskell function. FF. I will call it FF. So what FF should do, if I apply FF to the previous approximation, it gives me the next approximation. So if I apply FF to the previous approximation fact n, it will give me fact n plus 1. So I want a higher order function FF which produces new refinements. My first approximation will be the completely undefined function, fact 0. If I apply FF to fact 0, then I want to get fact 1. If I apply FF to fact 1, then I want to get fact 2, and so on. So I don't want to come up with these approximations myself. I want a Haskell function which does this for me. Now, how can I program this function FF in Haskell? It's not so difficult. Let's program it in Haskell. So what this function should do is, it should take an approximation to the factorial function and give me another better approximation to the factorial function. So it's ff is a function which takes an approximation to the, sorry, this is a Haskell function. So it takes a function from int to int. This is the current approximation to the factorial function. And it gives me a new function from int to int, which is the better approximation to the factorial function. Okay, and how would you define ff? So ff takes a function as input. This is the old approximation to factorial. And now from this old approximation, I want to get a new approximation, which is better. How can I get this? Well, let's look at the definition of factorial and at the definition of these approximations. For example, assume you want to get, you have fact 1 and you want to get fact 2. So if we apply ff to fact 1, we want to have the definition of fact 2. So if we apply to fact 1, we want to get something like the right-hand side of fact 2. Okay, let's copy the right-hand side of fact 2. So this is the right-hand side of fact 2 and of fact 1 and of fact 3 and of fact itself. So this definition looks almost the same. So it's lambda x if x is less than or equal than 0, then return 1, else. Now, the question is what happens now? Now we would, if we want to compute fact 2, then here we would have to use fact 1. So in other words, if fact 1 was our old approximation, and we want to compute the new approximation, then here, instead of a recursive call, we should use this old approximation. So in other words, if g is our last approximation and we want to get a better approximation, then we take the right-hand side of factorial, but instead of the recursive call, we use this old approximation. So what happens here is we take g of x minus 1 times x. So in other words, this is the right-hand side of fact. The only difference is that we substituted fact by this function variable. This is the only difference. So the right-hand side, this is the right-hand side of fact, but the recursive call of fact was substituted by g. Now, and this really does it. Suppose we apply ff to fact 1. So, I mean, this you can write down in Haskell, right? Fact 1 you can also define in Haskell. Therefore, you can also then write an expression like this, ff of fact 1. Now, what would happen if we apply ff to fact 1? This would be evaluated according to this definition. So ff of fact 1 is this right-hand side, but instead of g, you write fact 1. So this would be this lambda x stuff, blah, blah, blah. And then in the else case, g would be instantiated by fact 1. Fact 1 of x minus 1 times x. Now, and what is this? If you look at the definition of fact 2, you can see this is the right-hand side of fact 2. So this is nothing else but fact 2. And similarly, if you apply ff to fact 2, you get the right-hand side of fact 3. So indeed, this function ff, if you apply it to fact 1, then you get fact 2. If you apply it to fact 2, you get fact 3, and so on. And of course, now we know how to get this function in general. If we don't have factorial but some other function, we can get a corresponding higher order function by simply taking the right-hand side and replacing the recursive call by a function variable. So this is a method that always works. For any recursively defined function, we can produce such a higher order function which looks like this. And now we know how this chain of functions can be obtained. fact 0 is therefore nothing else but applying ff 0 times to the completely undefined function. So fact 0 corresponds to 0 times ff applied to the undefined function. Fact 1 corresponds to 1 time ff applied to the completely undefined function. Fact 2 corresponds to ff applied 2 times to the completely undefined function, and so on. Now to keep that now, sorry, to keep, yeah, okay, this is a bit of mixture between syntax and semantics, but therefore I didn't write equal, but corresponds to. But that's the basic idea. We start with the undefined function. This is the undefined function, and that's our first approximation. If we want to get approximation number 0. If we want to get approximation number 1, we apply this higher order function once. If we want to get approximation number 2, we apply it twice, and so on. So what we did here in this alternative 1 if, let's say, ff underlined is the semantics of this thing, this Haskell function ff, then we define the semantics of the Haskell function fact as the least upper bound of we had f0, f1, f2, and f0. So f0 was the semantics of fact 0. So f0 is now the semantics of ff applied to bottom 0 times. f1 is the semantics of ff applied to bottom 1 time. f2 similarly 2 times, and so on. So instead of defining the semantics of fact as the least upper bound of f0, f1, f2, and so on, we can also say it's the least upper bound of these things here. So it's the least upper bound of semantics of ff applied to bottom 0 times, 1 times, 2 times, and so on. So this is the same. This is just a different way of writing things down, but now it's more systematic because we know how to find these approximations. So to find these approximations, what we can do is we first build this higher order function. So if we have something like fact, we build a higher order function like this thing here, which we get from fact by replacing the recursive call by a function variable. And now we take, these things are not recursive. ff is not called recursively over there. So the semantics of ff we can determine. And I called the semantics of ff underlined. And now we build a chain. Ff underlined applied 0 times to the completely undefined function, then applied 1 time to the completely undefined function, applied 2 times to the completely undefined function, and so on. So I get this chain. This is the same as f0, f1, f2, what I wrote down before. And we take the least upper bound of this chain, and that's the semantics of fact. Now, indeed, this thing is the same thing as this. It's just different notation, but it's more systematic because we can determine this ff in a systematic way for every Haskell function. So a higher order function like ff can be determined in a systematic way for any Haskell function. So let me again summarize this alternative variant of defining the semantics. So first step would be define a higher order function which would refine approximations, so which can be used to build more and more refined approximations to the original functions, which can be used to compute more and more refined approximations. So in our example, this was this function ff, can be immediately obtained from the original function definition, from the definition of fact. And then step 2 would be find out the semantics of f, determine the semantics of this higher order function, Now this is possible because this higher order function is not defined recursively. So in our example, it would be the semantics ff underlined. And then the third step would be define the semantics of the original function as the least upper bound of 0, applying this thing 0 times to the undefined function, 1 times to the undefined function, 2 times to the undefined function, and so on. Now in our example, maybe we should write down this ff underlined. So what is the semantics of this ff function up there? So this ff function, this Haskell function up there, the semantics is some function which works on mathematical objects. I called it ff underlined. So what does it do? It takes a function and gives us back a function. It takes one approximation like fact 1 and gives us back another approximation like fact 2. So the input is a function from z bottom to z bottom, and the output is also a function from z bottom to z bottom. So how would this be defined? So if g is a function from z bottom to z bottom, so this is a function from z bottom to z bottom, then ff underlined applied to g is also a function from z bottom to z bottom. So how does it look like? Well, if we apply this whole thing to some element of z bottom, then we get something from z bottom back. And what we get back, well, we can immediately see from its definition. Now, if you look at this topmost board, you can see what happens. If ff is applied to g, to a function g, and then you apply the outcome to an integer x, then, well, we know the semantics of all this stuff on the right-hand side because it's not recursive. If x is less than or equal to 0, then the result is 1. So the result is 1 if x is less than or equal to 0. And otherwise, it's g of x minus 1 times x. So otherwise, it's g of x minus 1 times x, otherwise. So this semantics you can immediately get from the definition of ff, because apart from predefined things like minus and times and if, there is nothing in the right-hand side. So this is immediately obtained from the Haskell definition of ff, since ff does not use recursion. Now maybe you recognize this example. We had this at the end of the last lecture, and that's also on the current exercise sheet. One of the exercises of the current sheet is you have to prove that this thing is continuous. Now that's not so difficult because you can use the theorems of the last lecture for this. But so this has a motivation why this is interesting. This happens to be the function which transforms one approximation into the next approximation for factorials. So that is where this example comes from. Okay, so this is one way to define the semantics of recursively defined functions. You build this higher order function, which you get in a systematic way. You determine the semantics, which is easy because you just have predefined functions on the right-hand side. And then the semantics of factorial is the least upper bound of this chain. And we have already seen, well, this thing is the same as f0, this is the same as f1, so the least upper bound is indeed the factorial function on integers. Okay, so this is one alternative to define it. Now comes the other alternative. So this is alternative 2. So alternative 2 to define the semantics of fact. Now, as you might remember, part of our motivation was we had this definition of fact here, and we said, well, the semantics should be a function on integers which satisfies this equation. So in other words, it should be a function that where the right-hand side and the left-hand side somehow do the same thing. So the semantics of fact should be a function, some function g, which satisfies the defining equation of fact. Now, what does this mean? So with satisfying this defining equation of fact, it means whether I take this function g or whether I take the right-hand side where fact is replaced by g, that should be the same. So in other words, g should correspond to the right-hand side. So lambda x, if x is less or equal than 0, then 1, else g of x minus 1 times x. So g, so here we have g and there we have g. So this is g and this is g. So g should satisfy this equation. G should be the left-hand side. If fact is really replaced by g, then the left-hand side and the right-hand side should be the same. Now, this thing this is the right-hand side of factorial, of the fact definition, but fact has been replaced by g. Now we have already a function which does something like this. It gives us the right-hand side of the fact definition, but replaces the recursive call by g. We have called this ff. So this is ff of g. So in other words, the semantics of factorial should be a function where a function g where g is the same as ff of g. So here again I write corresponds because this is again a not very precise mixture of syntax and semantics. So whenever this occurs, this means this is just for intuition. There's some semantics and syntax are mixed here. To make it more formal, this means, so we look for a function g. The semantics should be a function from z bottom to z bottom. where we now also take the semantics of ff, where g is the same as the semantics of ff applied to g. Because this is the semantics of this ff function up there. And what we want is that g satisfies the defining equation of fact. In other words, whether we take the right-hand side of fact and replace fact by g, or whether we take g itself, this should be the same thing. Okay, if you look at this, ff of g should be g. Something like this is called a fixed point. So in other words, g should be a fixed point of ff. So in general, if you have a function, then an argument is called a fixed point if applying the function to this argument gives you this argument again. So in general, x is a fixed point of a function f if and only if f of x equals x. So this is the notion of fixed point. And here we want that g is a fixed point of this higher order function that we get from the definition of fact. Now, let me wipe the board and then I continue with the explanation. So the new alternative to define the semantics would now be the following. We again determine this higher order function, ff. Then we find out the semantics, ff underlined. And then we look for a fixed point. We don't build this chain and look for a least upper bound. Instead, we look for a fixed point. Now, this is not yet completely satisfactory. Let's look at another example. So, to see that this idea of fixed point semantics needs some more improvement, another example to show what is missing when we define semantics via fixed points. Okay, so we apply this idea to another simple example. It's the following Haskell function non-term, which we also had before. It's a function from int to int. And non-term is defined like this. You take an integer x and you return non-term of x plus 1. Okay, now if you look at it as a Haskell programmer, you know, of course, what will happen if you call non-term with some argument. As the name suggests, it will not terminate. So non-term, if you call non-term 0, you get a recursive call non-term 1, then you get non-term 2, non-term 3, and so on. Now let's see what comes out if we define the semantics like this. I mean, our intuition is this should be undefined everywhere. Now let's see whether our semantics gives us this result, and if it doesn't give us this result, then we have to think about the way we define the semantics, and something is not yet satisfactory. Okay, so to define the semantics, what did we do? We came up with this approximation function, and this approximation function takes an approximation to non-term and gives us a better approximation to non-term. So I called it ff for factorial, now I call it nn for non-term. So this approximation function I will now call nn. We can program it in Haskell. Now what type does it have? It takes an approximation to non-term and it gives us a better approximation to non-term. Now approximations to non-term have the same type as non-term. So it takes a function from int to int and it gives us a function from int to int. Okay, so how does it look like? Now nn takes some function g as an input. This is the old approximation and it gives us a new approximation. How does this new approximation look like? Well, we get this definition from non-term by taking the right-hand side, but by replacing the recursive call by this function variable. So it's the function which takes x, but now you take, instead of the old recursive call, you take this old approximation, g of x plus 1. Okay, so what is the semantics of nn? It is a function, let's call it nn underlined. It's a function nn underlined, which takes a function from z bottom to z bottom and returns a function from z bottom to z bottom. Okay, so if I apply nn underlined to some function g, I get another function from z bottom to z bottom. Now g again is a function from z bottom to z bottom. So let's apply it to some x, where x is from z bottom. Now the semantics of this is easy to determine because on the right-hand side we have just predefined functions. We know what the semantics of plus, the semantics is addition, semantics of 1, that's the number 1, and lambda means it's a function. It's a function which takes an x and gives us back the stuff on the right-hand side. So here it gives us back g of x plus 1. Now, we have two ways of defining the semantics now. With alternative 1, we would build this chain of starting with the undefined function, then we apply nn underline once, and then twice, and then 3 times, and so on. So let's see what happens. So alternative 1, we would say the semantics of non-term is the least upper bound of. First we take the undefined function. This is the undefined function from z bottom to z bottom. Then we take nn applied once to the undefined function. Then we take nn applied twice to the undefined function, and so on. Now, what is this? This is the undefined function from z bottom to z bottom. If we apply nn underlined to the undefined function, what do we get? We get a new function. The new function nn underlined applied to the undefined function. It's a function, if you apply it to some x, it gives you undefined function applied to x plus 1. Undefined function applied to something is always undefined. So if you apply nn to the undefined function, you get the undefined function again. Okay, so this is also the undefined function. And if you do it twice, you get also the undefined function, and so on. So this chain only consists of the undefined function. If you take the undefined function, you apply nn underlined to it, you get the undefined function again. So the semantics is the least upper bound of this chain, which is the undefined function from z bottom to z bottom. Now that's fine, because this is what we would have expected. If we see this Haskell program, then the semantics should be the function which is undefined everywhere. So alternative 1 leads to the right result. Now let's look at alternative 2. Alternative 2 says the semantics of non-term is the fixed point of nn underlined. Now, what is a fixed point? A fixed point means that nn underlined of g equals g. And here g is from z bottom to z bottom. Now, how do fixed points of nn underlined look like? Now, nn underlined is a function which takes g and then takes an argument and gives us g of x plus 1. So instead of writing this, we can also say nn of g. If these two functions are the same, this means they are the same on all arguments. So this should hold for all x from z bottom. So g is a fixed point if this holds for all arguments z bottom. Now this means g of x plus 1. So g is a fixed point if g of x plus 1 equals g of x for all integers x, also for bottom. Now, what functions have this property? All constant functions have this property. So, all constant functions are fixed points of nn. So in other words, this definition is ambiguous. It can happen that something like nn has many fixed points. Here we have infinitely many fixed points. And so it's not clear which fixed point should we take. For example, the constant function which always returns 17 is a fixed point. If you take this function, which always returns 17, and you apply nn underline to it, you get the same function back. But this is not this, we don't want this as the semantics of non-term. If we define the semantics of, if you write this in Haskell, and then the semantics is something which always returns 17, you would be very surprised. I mean, if you program this, and then you call non-term 0, and Haskell gives you back 17, you would be very surprised. So this is not what we want. So the question is, which of these fixed points do we want? It can happen that nn has many fixed points, and the solution is we want the smallest. We want the fixed point that is as undefined as possible. So take the least fixed point, or the smallest fixed point. So this is the fixed point that is as undefined as possible. And we note this by LFP, for least fixed point of nn. Okay, and now what is the least fixed point in our example? So all constant functions are fixed points. So here, the least fixed point of nn is also a constant function, but it should be less defined or equal than all other constant functions. And now there's just one solution. This must be the function which is undefined everywhere. So least, again, means least with respect to the less defined or equal relation. So this is the smallest function, the function that is as undefined as possible. And the motivation for this is, why should this be 17? This definition gives us no justification for returning the value 17. So whenever it's not enforced by the definition that stuff should be defined, then we say it should be undefined. If the definition doesn't force us to return something which is defined, then we want it to be undefined. So this is maybe the general philosophy here. So the reason for taking the least fixed point is the semantics should be undefined should be as undefined as possible. It should be undefined unless the function definition really forces us to make it defined. Unless the function definition forces us to make it defined. So now we see what alternative 2 would be. Alternative 2 is same first two steps are the same as in alternative 1. So determine a higher order function which computes approximations. So computing approximations. So this would be something like FF or NN. Then step 2 would be determine the semantics of this higher order function. Of this higher order function. So this would be FF underlined in the factorial example or NN underlined in the non-term example. And then step 3, in alternative 1, we would take the least upper bound of FF or NN applied 0 times to bottom, applied 1 time to bottom, and so on. And in alternative 2, we take the least fixed point of FF, or if we have NN, then we take the least fixed point of NN. And we have seen that in our examples, at least for factorial and for non-term, alternative 1 and alternative 2 lead to the same result. And that's no coincidence. They always give the same result. So it doesn't matter if we define the semantics like this or if we define the semantics like that, it gives us the same result. This is the fixed point theorem. Which is probably the most central theorem in the lecture, and we will prove this in the next lecture. It's very easy and short proof, so this doesn't take us longer than 10 minutes. But this theorem is also needed to make sure that this stuff always exists. So it makes sure this least fixed point really exists because it is this. The least fixed point you can obtain as the least upper bound of this chain. And now in this way we have now an idea how to define the semantics of recursively defined functions. The central idea is to get this higher order function which computes approximations. And then whether you take its least fixed point or whether you build this chain is the same. This leads to the same result. We will do this on Tuesday, and I wish you a nice summer party this afternoon, because this afternoon is summer party of computer science, in case you didn't know. And then we see each other again on Tuesday.